Hey darlings, welcome to our video on temperature. Here we're going to be kind of going through what temperature is. It's part of Unit 3. So you'll need your notes, which is pen and paper. We'll quickly look at tables S and T. You'll need a calculator, so make sure you grab a calculator that you use for Regents, not your cell phone. And we'll also need the Unit 3 packet. We'll do calculations in there. So in this lesson, we'll go through what the definition of temperature is, what thermometers are, the different temperature scales and conversions, and we'll go through a whole bunch of temperature calculations towards the end of the video. So, definition of temperature. Many people think of this as heat. Heat is the transfer of energy. Temperature, instead, is actually a measure of average kinetic energy. Notice that in my notes here, average kinetic energy is in red. Make this big and bold in your notes. It's a great way to answer some multiple choice questions. So, kinetic energy is just the energy of motion or of moving particles. The higher the temperature is, the more kinetic energy there are. So, the more motion of the particles that there are. The example here is that if we increase the heat, the temperature increases, which increases the average kinetic energy of the particles, and that increases the speed of the particles. We have a simulation from PhET, which is through the University of Colorado. If you haven't seen any of the University of Colorado simulations before, make sure you take a look at them. This one's on gas properties, and you could actually just look at this on your own computer as well. Just Google PhET, P-H-E-T, Colorado, and scan them to find the ones for gas properties. So here we have a container. There's a little guy kind of holding on to that container. Above the container we have a thermometer. It's measured in 0K, which is actually Kelvin. To the right of the container we have a pressure reading, and then we have a pump to add in some more gas particles. Below we have heat control, so I can add heat or remove heat. And then all the way on the right hand side I have parameters that I can set. I'm actually going to keep a constant volume in here. And down below, or the little box that's in here as well, I can actually measure the average speed. So I'm going to add in some particles. So I've got 165 particles according to the little box that I have here. And take a look at the temperature. It's 300 K. And the average speed is around 420 meters per second. So if you notice, the particles are moving in straight line motion. They're bouncing off of one another. They're bouncing off of the container as well. And I want you to take a look at the average speed of the gas particles as I add some heat in. So I'm adding some heat. The temperature is going up above 600 Kelvin. The speed's around 800 meters per second. Right now we're at 1000 Kelvin, and so we've increased the speed when the temperature increases. And take a look at the particles. They are moving very, very quickly. They're bouncing off of one another. That pressure also has increased as well. Now I'm going to remove some of the heat. So I'm adding ice to this. And the temperature is decreasing, the pressure is decreasing as well, and the speed is decreasing. Let's take a look at the particles themselves. So before they were moving really, really quickly, now they're just slowing down. We're down to below 30 Kelvin. This is way cold. That speed is in the 70s, 70 meters per second. So if you look at the particles themselves, they are barely moving. The speed is around 25 meters per second, and we're going down to 0 Kelvin. That's the smallest that we can go to, or the lowest we can go to in the Kelvin scale. And take a look at the particles. They're barely moving. They're just vibrating at this point. And the speed is around 13 meters per second here. So we can see from this simulation that we can actually change, when we change the amount of heat added, the average kinetic energy will change. Alright, so we've done that on these notes, and if you missed any of these notes, make sure you pause the video to grab them. And I'm sorry that my video or my computer is going pretty slow. It's pretty old right now. Alright, so don't forget to make sure that you grab all of these notes from here. And Google that PhET simulation if you like. Here is a multiple choice question from the Regents. Actually, I have one above this one. Let's take a look at this one first. one below that. There we go. The temperature of a sample of matter is a measure of. So right here, key word is temperature. When we think temperature, automatically think average kinetic energy. Not just kinetic energy, but average kinetic energy. So let's take a look at how they're trying to trick us here. A says average kinetic energy, B says average potential energy, C says total kinetic energy. Oops, sorry about that, darlings. Total kinetic energy, and D says total potential energy. So we definitely know it's not potential energy, and it's not total kinetic energy, it's average kinetic energy. So A is our correct choice. The next question, which sample of ethanol has particles with the highest average kinetic energy? Hey, key in on average kinetic energy. Whenever you see that word, you can cross it off and write temperature instead. And I want you to do this on your multiple choice questions too. So instead, reread this. Which sample of ethanol has particles with the highest temperature? Looking at all of these, we know it's dealing with ethanol, so that we can get rid of. And here we have a measure in milliliters volume. And here we have degrees Celsius. They're trying to trick us with these milliliters. They're trying to say, ooh, let's see if they get confused by adding 10 milliliters versus 100 milliliters. None of those milliliters matter because we're just dealing with temperature. So here we want the highest temperature, which ends up being B, 55 degrees Celsius. And let's take a look at this question. A flask containing molecules of a gas, A, and a separate flask containing molecules of gas, B, are both at the same temperature. So temperature is there. Gases A and B must have equal. So you see temperature here. What should you automatically think? D, average kinetic energy. Alright, so let's take a look at thermometers. We know we can measure the temperature using thermometers, but we need to make sure we have two fixed points. I don't know why the I is not in fixed. I apologize. Make sure you put that in there. Generally put the freezing and boiling points of water in there. So see, here I have a beaker with some ice water, and it's at 0 degrees Celsius. On the right, I have two temperature scales. The left-hand side has Fahrenheit, and the right-hand side has Celsius. So let's look at the major things that we need, two fixed points essentially here, when water freezes and when water boils. In Celsius, it's 0 degrees Celsius. For water freezing, it's 32 degrees Fahrenheit when water freezes. When water boils, it can be at 100 degrees Celsius or 212 degrees Fahrenheit. I don't know about you, but I'd rather deal with 100 and 0 over 32 and 212 degrees Fahrenheit. Those are, from 0 to 100 is just an easier way to kind of remember those fixed points. One thing I want you to make a note of right now is that if you take a look at Table S, we have the melting point and boiling points of all of those elements listed for you. They're in Kelvin, or K, and we'll talk about what that is in just a bit. The melting point. For melting, we know we go from a solid to a liquid, so make sure you write that down in there. It also is the same temperature as going from a solid to a liquid as well. Boiling point, we go from a liquid to a gas, and it's the same as going from a gas to a liquid. Make sure this gets down on Table S. I'll be looking for that. So your temperature scales. We've used Fahrenheit here in the United States. They'll use it in other countries such as Belize. And water freezes at 32 degrees Fahrenheit, which we experience here in the North Country far too often. And water boils at 212 degrees Fahrenheit. Celsius is used by all of the other countries, and it's also used in science. So water freezes at 0 degrees Celsius, and then water boils at 100 degrees Celsius. Kelvin is something that you may not have seen before. We use this here in chemistry, especially when we're talking about gases. It starts at 0 Kelvin. Water will freeze at 273 Kelvin, and water boils at 373 Kelvin. So two things I want you to make a note of. First, Fahrenheit and Celsius each have a degrees sign. Kelvin does not. There is no degrees Kelvin. It's just K. Next, if we look at the difference between water freezing and water boiling in Celsius, that's 100 degrees. If we look at water freezing and boiling in Kelvin, that's also 100 degrees, okay, or a factor of 100. So Celsius and Kelvin are pretty much in that same type of scale. So when we have the three thermometers together, we have Fahrenheit, Celsius, and Kelvin. We can take a look at some key points. One is absolute zero. It's all the way down here. Notice absolute zero is actually going to be 0 Kelvin. There is no negative Kelvin. If we remembered actually from that simulation, that Kelvin stopped at 0, that was the bottom it could be, and those particles were barely moving. So absolute zero is actually when particles stop moving, and that's at 0 Kelvin. So Kelvin is based on that particle motion. That's why it's super important here in chem. With water freezing, 32 degrees Fahrenheit, 0 degrees Celsius, and 273 Kelvin. And then water boiling at 212 degrees Fahrenheit, 100 degrees Celsius, and 373 Kelvin. So the things you need to remember, absolute zero is 0 Kelvin. Water freezes at 0 degrees Celsius. In fact, let's make sure, let's get all of that in there. And water boils at 100 degrees Celsius. From knowing these degrees Celsius values, we can calculate what the kelvins are. So you don't need to memorize these Kelvin values. In fact, let's go ahead and look at the calculations here. We have, and you've probably done this before, from Fahrenheit to Celsius, or vice versa. Degrees Fahrenheit is equal to 9/5 degrees Celsius plus 32. We have a fraction here. I know that scares some of you guys, so hey, punch 9/5 into your calculator. Go ahead and do it. You should see it's 1.8, which is not a big deal. Alright, so if you're not comfortable with a 9/5, make it 1.8 instead. It's the same thing. And we have here, Kelvin is equal to degrees Celsius plus 273. So whenever you have, whatever that Celsius is, add 273 to get you to Kelvin. Let's go back. Okay, so if I had, let's see, where's water freezing right here? 0 degrees Celsius. Let's go back. Sorry, darlings. 0 degrees Celsius. If I add 273 to it, I get to Kelvin. Hey, there we go. Same thing with water boiling. If I'm in degrees Celsius, I add the number 273 to it. And hey, look, I get 373. And that calculation for Kelvin and degrees Celsius is on table T. So no need to memorize it, it's there for you. What we do need to do is actually be able to rearrange the formulas. I know this scares you guys, but it's just like what you do in math class. Even though we don't use x and y as variables, we'll use c and f and k. That's the same thing. It's okay. So here we want to rearrange the formula to find degrees Celsius when we're given degrees Fahrenheit. So we can actually just use that first formula. Fahrenheit is equal to, we'll change it to 1.8 just to make you happier, degrees Celsius plus 32. I want to find Celsius, so I want to get Celsius all by itself. So I'm going to rearrange the entire formula to get Celsius all by itself on one side of the equation, or to get C all by itself. So just by looking at the math, I know I can subtract 32 first. So subtract 32 from both sides. That's equal to 1.8 degrees Celsius. And that degrees, just think of it, it's okay. Make it C. That's fine with me. But we know that you're multiplying it. So now I can get rid of 1.8 just by dividing both sides by it. So F minus 32 over 1.8 is equal to degrees Celsius. Okay, so I can easily rearrange that equation. So if I'm given Fahrenheit, I can find Celsius by doing that. The next thing is rearrange the formula to find Celsius when given K. So here I can go back to table T. I know Kelvin is equal to 273 plus Celsius. I want to be able to find Celsius, so I want to get Celsius all by itself on one side of the equation. So subtract 273 from both sides. K minus 273 is equal to degrees Celsius. Next, rearrange the formula to find K when given degrees Fahrenheit. So here I need to find or use both formulas. So if I have the first formula, F is equal to 1.8 times degrees Celsius plus 32, and then the other equation I have is Kelvin is equal to 273 plus degrees Celsius. Well, I know that I have C in common for both of these. In fact, I just isolated them. So I'm going to go ahead and grab that from what I had before. C is equal to F minus 32 over 1.8 on this side. And on the right-hand side, C is equal to K minus 273. So I can actually take both of these equations and make them equal to each other because I have C right here. So these two will be equal to one another. F minus 32 over 1.8 is equal to K minus 273, transitive property. Alright, so I want to find K when given F. So I want to get K all by itself. Pretty easy to do. Just add 273 to both sides. F minus 32 over 1.8 plus 273 is equal to Kelvin. There you go. And, whoops, look, I'm running low on battery power. Hopefully we have enough time here. So rearrange the formulas to find degrees Fahrenheit when given K. I can use that same equivalency that I had before, where I had Celsius is equal to F minus 32 over 1.8, and I had Celsius is equal to K minus 273. I can make these equal to one another. So F minus 32 over 1.8 is equal to K minus 273. This time I want to get F all by itself. So let's see, we'll do a little bit more math here. Not too big a deal though, right guys? Multiply both sides by 1.8. That cancels this 1.8. So I have F minus 32 is equal to K minus 273 times 1.8. And now I want to get the F by itself. I can add 32 to both sides. So I have F is equal to 1.8. Keep the K minus 273 in parentheses, plus 32. Okay, so here I've rearranged the equations. Next, I can use these equations to plug in some values. So I have 0 degrees Celsius. I want to figure out what the Kelvin is. And hey, we kind of already done this before, haven't we? 273 plus degrees Celsius is equal to Kelvin. So 273 plus 0 means that K is equal to 273. Okay, so I'll put that right in there. Here, 0 degrees Celsius is equal to some amount of Fahrenheit. Living in the North Country, again, we know that 0 degrees Celsius is 32 degrees Fahrenheit, but let's just prove it. We have F is equal to 1.8 times degrees Celsius plus 32. So I can do 1.8 times 0 plus 32. Get rid of that. F is equal to 32. Yep, we know that. Good. Alright, 212 degrees Fahrenheit is equal to something degrees Celsius. So we know we have F is equal to 1.8 times degrees Celsius plus 32. Let's make that a little bit nicer. 32. And I want to get Celsius all by itself when I rearrange the equation. So I have F minus 32 is equal to 1.8 times degrees Celsius. Divide both sides by 1.8. 1.8. So F minus 32 over 1.8 is equal to degrees Celsius. And then I can plug in 212 right in for F. So 212 minus 32 over 1.8 gives me degrees Celsius. Plug this into your calculator. And I should see that this should be equal to 100 degrees Celsius. Right there. Alright, so let's move on to 2D. So we have 212 degrees Fahrenheit is equal to an unknown amount of Kelvin. And I remember we rearranged all these equations before, so let's go ahead and use those. Kelvin is equal to F minus 32 over 1.8 plus 273. So let's kind of actually pause and make sure that our answer will make sense. We have 212 degrees Fahrenheit. Will this be a lower or higher number of Kelvin? So when we're in Fahrenheit to Kelvin, we should know that when we're at 212, the Kelvin value should be higher. Okay, so let's make sure that we can do that in here. So 212 minus 32 over 1.8 plus 273. Punch this into your calculator. You do the numerator first, 212 minus 32, press enter, divided by 1.8, press enter again, plus the 273. This ends up being 373 Kelvin. Okay, so go ahead and put that in. Good, our Kelvin temperature is higher than our Fahrenheit temperature. Alright, let's look at E. So here we have an amount of Kelvin, and we want to figure out what the Fahrenheit is. So Kelvin's pretty high up there. Make sure your Fahrenheit's a little lower at the end. And we will go ahead and use those rearranged equations from before. So your F is equal to 1.8 times K minus 273 plus 32. So your 1.8 times 450 minus 273 plus 32. So remember PEMDAS, do your inside your parentheses first, then multiply it by 1.8, and then add in your 32. So here we end up getting 350.6 degrees Fahrenheit. And when I give you these lines, guys, make sure you put your answers in those lines as well. And I'm looking for all of this work. So to get credit, you need your formula, plugged in values, and then your final answer boxed with units. Alright, F, 450 Kelvin is equal to something degrees Celsius. So let's use our equation. Kelvin is equal to 273 plus degrees Celsius. I want to find out what the degrees Celsius is, so I'm going to highlight it and get Kelvin all by, get Celsius all by itself. So I have Kelvin minus 273 is equal to degrees Celsius. So we have plugged in values, 450 minus 273 is equal to degrees Celsius. So from here we should see it's 177 degrees Celsius. Alright, so 177. Again, I have my formula. My rearranged formula here. Plug them in. And the final answers boxed and with units. Good. Alright, then I have G, 98.6 degrees Fahrenheit, close to body temperature, is equal to something degrees Celsius. So my formula was Fahrenheit is equal to 1.8 times degrees Celsius. I'm putting parentheses in here. It's the same thing. I'm just kind of putting them in just to make sure that you see them. Alright, let's rearrange the equation. So F minus 32 is equal to 1.8 degrees Celsius. Divide both sides by 1.8. So F minus 32 over 1.8 is equal to degrees Celsius. So let's plug in those values. 98.6 minus 32 over 1.8 is equal to degrees Celsius. Do your numerator, then divide by the bottom. So Celsius ends up being 37 degrees. Okay, and so here we have 37 degrees. I have my rearranged formula right here, plugged in values, and the answer with units and a box around it. Alright, so 2H. Go ahead and pause me, do this one on your own. Okay, so I can use the value that I had from before for degrees Celsius, because, hey, 98.6 degrees Fahrenheit, that's the same thing as I wanted before, except this time into Kelvin. Where am I? There we are. Or I can just use those rearranged or plugged in values. So K, my rearranged formula is F minus 32 over 1.8 minus 273. Okay. Sorry, plus 273. Make sure you put that in there. Plug in all your values. 98.6 minus 32 for 1.8 plus 273. Punch this into your calculator. And we should get 310 Kelvin. Okay, so here I have my rearranged formula, my plugged in values, and my answer with the box and units. Alright, almost there, darling. So, negative 40 degrees Celsius into Fahrenheit. So I'll take that same equation. Fahrenheit is equal to 1.8 degrees Celsius plus 32. And we want to be able to get, let's see, we want to solve for Fahrenheit. So we can just go ahead and use that same equation. 1.8 times a negative 40, or sometimes we can put these in parentheses just to make it easier, plus 32. So punch this into your calculator. Alright, notice here you have negative 40. Wait a minute, negative 40 degrees Celsius is equal to negative 40 degrees Fahrenheit? Actually, when you look at the scale, these two values end up lining up. So all those numbers that we can have for Celsius and Fahrenheit, these two end up being the same. Alright, and let's figure out what that is in Kelvin. So we can take our equation. Kelvin is equal to 273 plus degrees Celsius. So 273 plus a negative 40, or 273 minus 40, should give you 233 Kelvin. Okay. Alright, we've got the arranged equation, plugged in values, the final answer with units, and a box. Alright. So, to quickly summarize, temperature is a measure of average kinetic energy. Thermometers and temperature need 2 points, 2 fixed points. And you'll use table T for temperature conversions between Celsius and Kelvin. If you need something for Fahrenheit and Celsius, I will give you that formula. You just need to be able to rearrange the equations. So hopefully you guys have a great day. Take care and let me know if you need any help. Bye.